Okay, so finally we're reaching this mysterious notion of isomorphism that we've mentioned several times, but we're ready for the formal definition. So here goes. Let V1 and V2 be two vector spaces over the same field. Whenever we want to discuss relations between vector spaces, they have to share the same scalars. So over the same field F, V1 and V2 are called isomorphic if there exists a linear map, a linear transformation, let's call it T, from V1 to the other, V2, which is one-to-one and onto. One-to-one and onto. So two vector spaces are called isomorphic if there exists a map which is one-to-one and onto between one and the other, a linear map. That's the notion of being isomorphic. And T is called, such a map, T is called an isomorphism. So a map which implements the isomorphism is called an isomorphism, which gives the fact that they're isomorphic spaces. Okay? And the notation, out of space here, maybe let's add it up here, notation when spaces are isomorphic, we write V1 equals V2 with tilde above the equal sign. Okay? So let's give some examples before we discuss this a bit further. Let's give some examples. So here's our first example. Here's a map T going from R4 to M2R. So R4 is 4 tuples of real numbers, and M2R are 2 by 2 matrices over the real numbers. And the map sends an element of the form A, B, C, D. This is a general vector in R4, sends it to the matrix A, B, C, D. Okay? So the claim is that this map is an isomorphism, and therefore these spaces are isomorphic. Okay? So what do I need to show in order to say that this map is an isomorphism? I need to show that it's linear. And we already know this. I'm not going to verify the details. It's completely simple. Okay? One way to see it automatically is because each entry here is a linear combination of the entry here, but it's just the entry. So it's obviously a linear map between the spaces. It's obviously onto. Every matrix here can be obtained from a vector here. And it's obviously one-to-one. The only way to obtain the 0 element is if you start out with the 0 element, right? So why am I saying one-to-one and thinking about the 0 element? What does that have to do with one-to-one? Kernel, right? For a linear map to be one-to-one means that the kernel is trivial. Okay, so when I'm saying one-to-one and thinking about linear maps, I'm automatically translating my thoughts to what is the kernel. And the answer, the kernel, the guys that get sent to 0 in this case, 0 is the 0 matrix, is only the 0 vector. So the kernel is trivial, the map is one-to-one. So this is a linear transformation which is one-to-one and onto, and therefore it's an isomorphism between these two spaces. These two spaces are isomorphic. Okay? So this T is linear, one-to-one, and onto. And all of these facts are very easy to check, so I'm not going to write the details. We said them, okay? And therefore, these two spaces are isomorphic. R4 is isomorphic to 2 by 2 matrices over R. Okay? Here's another example. So let's call this example 1. Here's example 2. Let's look at the map T from 2 by 2 matrices over R to the vector space of polynomials of degree less than or equal to 3 with coefficients in R, real coefficients. And the map is going to be the map that sends a vector here, a general vector here is a matrix A, B, C, D, to the polynomial ax cubed plus bx squared plus cx plus d. Once again, very easy to verify that this map is a linear map, a linear transformation, and that it's one-to-one and onto for the exact same reasons that we mentioned previously. Any polynomial here can be obtained, just take the coefficients and put them in a matrix. And the only way to get the 0 polynomial is if you start out with the 0 matrix. Okay? So again, T is linear. T is linear. One-to-one and onto. And hence, R, M2 of R, M2 of R is isomorphic to R3X. Okay? So this idea that was around, that these three spaces are in fact, in some sense, the same space in disguise, in different disguises, is now put into formal words. These are not the same space. M2R and R3X are not the same. They're not equal as vector spaces, but they're isomorphic. Okay? And as far as linear algebra can see, they're the same. Okay? Their linear algebraic structure, their vector space structure is exactly the same. That's what the isomorphism means. Okay? Once you go beyond, they may be very different. These are functions, these are matrices. You can take a determinant of a matrix. We usually don't define a determinant of a polynomial. You can ask what is the derivative of a polynomial. We usually don't take the derivative of a matrix. So once you go beyond what linear algebra can see, then they're very different. But as far as their vector space structure, they're the same. That's the notion of isomorphism. Okay? Here's another example. Example number 3. This is a non-example. So there is no isomorphism between, let's say, R3 and M2 of R. Why is that? How can I say that in a very precise way? I'm not saying that I can't find one. I'm saying that there is no isomorphism. Okay? So something in the linear algebraic properties of these two vector spaces should be an obstruction to the existence of an isomorphism. an obstacle that cannot be passed. Okay? And what is that? What fails?
They're not the same dimension.
Exactly. Very good. Very good. They're not the same dimension. This is a vector space of dimension 4, and this is a vector space of dimension 3. And why is that crucial? Why is that crucial? We had a theorem that said if a map is one-to-one and onto, then the dimensions of the domain and the range have to be equal. Okay? And therefore, there cannot be a one-to-one and onto linear map between these two, because that would force, by the theorem, the dimensions to be equal, and they're not. Okay? So there is no isomorphism between these two spaces. They're not isomorphic. And the reason is, since 3, or let's write it like this, the dimension of R3, which is 3, and is not equal to 4, which is the dimension of M2R. So they have different dimensions, and we had a theorem that a one-to-one and onto linear map between two spaces forces their dimensions to be equal. Okay? Is this clear? Okay? So we formalized the notion of when two spaces that we felt are the same thing, when are they in fact the same thing as far as linear algebra goes. This is not an equal sign. This is an isomorphism sign, and that's what it means formally. I want to make a few remarks. So the first remark, this notion of isomorphism is what we call an equivalence relation. Okay? So isomorphism of vector spaces is an equivalence relation. What does that mean? So the notion of an equivalence relation, this is not something that I'm just making up right now. It's something well defined, and it's a way of saying that two things are equivalent in some sense. Okay? I'm not saying equal, I'm saying equivalent in some sense. Okay? And for two things to be equivalent in some sense, in the sense of being an equivalence relation, we're requiring some very basic properties to hold that would, otherwise it wouldn't make sense to say that they're equivalent. Okay? And the properties are the following. One is called, an equivalence relation is made up of 3 properties. Okay? One is symmetric. There's a double M in symmetric, right? So one is that it has to be symmetric. And what symmetric means is that suppose you have V1 isomorphic to V2. If you want to say that these two are equivalent, what does it mean that V1 is isomorphic to V2? By definition, all it means is that there's a map from V1 to V2, which is one-to-one and onto and linear. That's what it means. That's the definition. Okay? Does it imply that V2 is isomorphic to V1? Okay? If it wouldn't, then it would be kind of weird to say that they're equivalent in some sense. If one is equivalent to the other doesn't imply that it goes the other way. That would be weird. So this is the notion of symmetry in terms of an equivalence relation, and it holds for isomorphism. If there's a linear map, one-to-one and onto, between the two spaces, then that map is invertible, right? And therefore there's a map going the other way, the inverse map, which is again linear, one-to-one and onto, and therefore they're isomorphic the other way. Okay, so in fact, being isomorphic, it doesn't matter which one you write on either side of the equal sign. That's the notion of being symmetric. Another notion which is part of the definition of being an equivalence relation is transitive. Meaning the following. Suppose V1 is isomorphic to V2, R4 and M2 of R, and V2 is in turn isomorphic to some other space, V3, M2R and R3X. If this is an equivalence relation, it should hold that V1 is isomorphic to V3. Okay? And so if this is R4 and this is M2R and this is R3X, we know that there exists an isomorphism between V1 and V3. There is a map going from V1 to V3, which is linear one-to-one and onto. Okay? That's this fact. Why is it true? How do we know that? If you want to say that as a fact, you have to say, of course, we know it. If T gives the isomorphism here, and S gives the isomorphism here, what would give the isomorphism here?
TS.
Exactly, the composition. Okay, we know how to compose linear maps. We know that when we compose linear maps, what we get is again a linear map. We proved that. Those are things that we proved. And we know that in general, when we compose functions, if this one is one-to-one and onto, and this one is one-to-one and onto, so would be the composition. Okay? So here we're using the fact that we can compose linear maps. Here we use the facts that linear maps, which are one-to-one and onto, have inverses, and that the inverses are linear maps as well. Okay? So this is the property of being transitive, and the third property is the property of being reflexive, which means it may seem trivial, but sometimes it's not. In this case, it really is, that any space is isomorphic to itself. Okay? And what would implement the isomorphism of a vector space to itself?
It's the same space.
That doesn't mean they're isomorphic. What you're saying is a theorem.
Identity.
Exactly, exactly. Saying that they're the same space doesn't mean that they're isomorphic. Okay? It means so because there's a theorem. Okay? A theorem that says if two spaces are equal, then they're isomorphic. Okay? It sounds like a stupid theorem, but you need to prove it. And the proof is very simple. Take the identity map between V and itself. That would implement an isomorphism between the spaces. It's of course one-to-one and onto, and it's linear. Okay? So these are the three properties that hold for the notion of isomorphism of vector spaces, and then make that notion into an equivalence relation. Okay? We're going to see later today another notion of equivalence, a different notion of equivalence, a notion of equivalence between matrices, and again we're going to say that that's an equivalence relation. Okay? Is this clear? Is this remark clear? Okay. Good. So what I want to do now is prove a theorem. Not a hard one. That says the following. V is isomorphic to W if and only if, I'm assuming both are vector spaces over the same field of scalars. That's a standing assumption. If and only if they have the same dimension. Okay, so this is a pretty strong statement. It says that if you take two vector spaces and they have the same dimension, somewhere out there, there's going to be a linear one-to-one and onto map which gives the isomorphism between these two spaces, even if it's not easy to see automatically. Okay? So, in fact, having the same dimension, which is just kind of a little number that comes along with the vector space, how many vectors does it have in a basis, in fact, determines its linear structure. In the sense that if you take another space with the same dimension, they're the same space as far as the linear structure goes. They're isomorphic. Okay, so this is a pretty strong statement. Let's prove it. So now if you give me another linear space over R with dimension 4, I'm going to know that it's isomorphic to 2 by 2 matrices over R. It's isomorphic to polynomials of degree less than or equal to 3 over R. It's isomorphic to R4. They're all the same. The same in the sense of isomorphism. Okay. So how do we prove this? Well, we need to prove two things, right? This direction and this direction. Let's start with this direction. So I want to show that if they have the same dimension, then they're isomorphic. So let V1, V2, Vn be a basis for V, and W1, W2 up to Wn, and it's the same n because we're assuming that they have the same dimension, be a basis for W. Okay? So here we already use the assumption that they have the same dimension because we said, okay, we have two bases, but they have the same number of elements. Okay? So let's take these two bases. What am I trying to do? Let's pause a second, think. I'm trying to show that they're isomorphic. I'm going in this direction. To show that they're isomorphic, I need to provide a linear map that goes from one to the other. I have to say, what does T do to a vector V, right? And show that that map that I gave is in fact linear, one to one and onto. That's it. That's the definition of isomorphism. Let's look at it again. Okay. Two spaces are isomorphic if there exists a linear one to one and onto map between them, right? That's all. That's it. Good? So how can I give the map? This is something we've seen. Then the map T, which takes a general element here. A general element in V. What does it look like?
Linear combination.
Right, a linear combination of VI's. So it's alpha 1 V1 plus ... alpha n Vn. And what am I going to send it to? W.
A general element.
The same linear combination of the W's. Alpha 1 W1 plus ... alpha n Wn. Okay? The map T from V to W that takes a general element in V, which is a linear combination of the VI's, and sends it to the exact same linear combination of the WI's, is an isomorphism. How do I know that it's an isomorphism? This is a theorem that we proved. Okay, we proved that the map given by this is always linear, and that we had it in several parts, that theorem. The first part said, if you take any set of W's, not necessarily a basis, this map is going to be linear. And then if this is a basis, then it's not just linear, it's one to one and onto. This is the exact statement of the theorem that we had several lessons ago. Okay? Then this map is linear, one to one, and onto by a previous theorem that was precisely the statement of that previous theorem, and therefore, and hence, it implements an isomorphism T from V to W. Good? So If they have the same dimension, they're isomorphic. And I know precisely how to construct the isomorphism. Take a basis of one, a basis of the other, and define what T does to an element as precisely the same linear combination of those, of the basis elements of the other. Okay? That's one direction. Now I need to prove the other direction, that if they're isomorphic, then they have the same dimension. Okay. We're going to need a new board for that. So maybe let's erase this remark. So this direction, continuing the proof. So now we're assuming that they're isomorphic and we want to show that they have the same dimension. So let V1 to Vn be a basis for V. I can't take W1 to Wn a basis for W because I don't know that W is of dimension n. Right? That's what I want to prove in this direction. So I'm assuming that V has dimension n. I want to show that that's the dimension of W. What can I hang on to? What do I know? What do I have control of? What can I use? Right. There is an isomorphism. Right? There is a map called the map T. Okay? So what can I do using T? I can do T to these guys. And if I can show that when I do T to these guys, I'm going to get T of V1 up to T of Vn. If I can show that that's a basis for W, then I'm done. W has dimension n as well. That's what I'm going to do. So, so let's call this B. B is a basis for V, and denote A is going to be the set T of V1 up to T of Vn. A is a subset of W, right? It's guys in W, where T is an isomorphism. And that's the assumption of this direction, that there is an isomorphism between the two spaces. Good? Okay. So what I want to show is that this set A is a basis for W. If I can show that, it means that W has dimension n as well. It has a basis comprised of n elements. Okay? So what do I know without any additional statement? In order to show that it's a basis, what do I need to show?
That it's a minimal spanning set.
Okay, there are various ways of, but by definition, okay, before we go to theorems, I need to show that it's spanning, right? And that they're linearly independent. That's being a basis, being a spanning set and being linearly independent. Is it a spanning set? Answer, yes. We had that theorem very, very long ago. That was one of the most basic theorems for linear transformations. You take a spanning set in the domain space, you T it, you get a spanning set for the image, right? Okay, so let's write that.
Didn't we have a theorem specifically stating that it's a basis in this case?
Not yet. That's going to be precisely this theorem. Okay, so by a previous theorem, maybe some of these facts have been mentioned or used in various inside proofs of other facts, but I don't think we had it written precisely like this yet. So by a previous theorem, A spans the image of T. That's the theorem that we had. You take a spanning set for the domain, you do T to its elements, you get a spanning set for the image, not necessarily for the entire range. Okay? But in this case, what is the entire range? W, and it's equal to the image. How do I know that it's equal to the image?
Because it's isomorphic.
Okay, so in particular?
Onto.
Right, exactly. T is an isomorphism, therefore it's onto. Therefore the image of T coincides with the entire range. So this set, which a priori only spans the image, in this case spans the entire range, since T is onto being an isomorphism. Do you agree? So it remains to show that this set A is linearly independent. If we show that A is linearly independent, we're done. Okay? And what property didn't we use? What should be the ingredient somehow in showing that it's linearly independent?
1 to 1.
That it's 1 to 1. We didn't use that fact yet, right? And that fact that it's 1 to 1 would probably translate to what property? Okay, but what's going to bridge that translation between being 1 to 1 and being linearly independent? What is 1 to 1? How do we think of 1 to 1-ness in terms of linear transformations? Trivial kernel, right? That is something you have to do automatically. 1 to 1, kernel equals 0. 1 to 1, kernel equals 0. Kernel equals 0, 1 to 1. Okay? It's not true for general functions. Don't do that in calculus. Okay? But in linear algebra, that's the same. Okay? Okay, so let's show that A is linearly independent. So how do we show that it's linearly independent? We need to take a linear combination of these guys that equals 0 and prove that all the coefficients are 0. That's the meaning of being linearly independent. So if alpha 1 t of v1 plus alpha n t of vn equals 0, if we take a linear combination of elements of A, which equals 0, we need to show that all these alphas are 0. That's what it means to be linearly independent, by definition, right? So if this equals 0, then we know by properties of a linear transformation that we can stick the alphas into the t and then take t of the sum. So this is the same as saying that t of alpha 1 v1 plus alpha n vn equals 0. This is just the property of being a linear transformation. Do you agree? T of a linear combination is the linear combination of the t's. Right? So if t of this is 0, what do we know? It's 1 to 1. Therefore, if something gets sent to 0, that something is in the kernel, but it's 1 to 1. The kernel is 0. So this implies then this, and therefore, so alpha 1 v1 plus alpha n vn is 0. Right? So let's write, since the kernel of T is just the 0 elements, that's the meaning of being 1 to 1. Okay? So here we have an element which is sent to 0. Being sent to 0 means it's an element of the kernel. But since T is 1 to 1, we're assuming in this direction that there is an isomorphism, so T is 1 to 1. Therefore, the kernel is trivial. Only 0 is in the kernel. Therefore, this element is itself 0. Do you agree? So this element, what is it? It's a linear combination of the VI's. The VI's were a basis for V. We know that they're linearly independent. So if we have a linear combination that equals 0, and this is a basis, it forces all the alpha i's to be 0. And thus, alpha I equals alpha 1 equals alpha 2 equals ... equals alpha n equals 0. And that's what we wanted to show. We took a linear combination of t of vi's, which was 0, and showed that all the coefficients have to be 0. Okay? So this is really, we just traced the definition of being linearly independent, okay, and used the powerful equivalence, the powerful fact that being one-to-one translates to having a trivial kernel. Okay? Okay, so this completes this proof. We proved both directions. Let's go back here for a second. What did we prove? We proved that the dimension of a vector space determines its structure as a linear space, in the sense that if you take two spaces with the same dimension, they're isomorphic. And if they're isomorphic, they have the same dimension. A corollary of this fact, and let's erase the proof and write it, and this is really how we think of finite dimensional vector spaces. Okay, and we've been using and saying a bit, what I'm going to write as the corollary right now, but it wasn't completely formal, and now it is. So corollary any or every vector space of dimension n over some field f is isomorphic to Fn, to n tuples over the field F. Okay? And the way we use this, the idea of this statement is by passing to coordinate vectors. Okay? When we had R3 of x, when we had polynomials of degree less than or equal to 3, we said, well, they're polynomials, they're functions, they have derivatives, they have integrals, they're really guys that live in calculus, right? But as far as their vector space structure, all we need is the coefficients. Okay? So we thought of this animal here, the vector space R3 of x. We said, well, in fact, elements are these guys, but in fact, we can think of them as R4. Okay? And the way to pass from here to here is just take the coordinate vector. We said, these are matrices, right? They have a meaning. There are things we do with matrices. We can take determinants. We can say what a rank of a matrix is. We can use them for solving linear equations and so on and so forth. There's a big, rich world of what we do with matrices. But as far as being a vector space, we can really think of them like this, the coordinate vector. So these two spaces, which are very different, are in fact isomorphic to R4. Okay? So that's that corollary. Every vector space of dimension n over a field F is in fact isomorphic to Fn. Okay? So this is where I want to stop this discussion of isomorphism. It's a key notion in anything that has to do with algebra. Okay? Here we only defined what isomorphism means for very specific structures, for vector spaces. But there's isomorphism of groups. Remember we mentioned groups. And there's isomorphism of fields. Okay? And any algebraic structure you can define what it means to be isomorphic, being the same structure in disguise. Okay? And what it usually is going to mean is that there's an appropriate map that preserves the structure, which is one-to-one and onto. Okay? So it's a much more general notion than just for vector spaces. We're discussing it here only for vector spaces. Okay, good. Questions? Okay, so what I want to do next, before we move on to a different point of view on this whole idea of linear maps and matrices, I want to discuss one more small notion, which in fact is not always part of the material in this course. So I'm going to devote a short lesson to something which may be only for your general knowledge. I think it's very important to at least encounter this. And that's, think of the space of all possible linear maps between V and W. Okay, so we're going to take one step up. Think of what we did here. We started with defining what is a vector space. That was a structure. Okay, so now we have vector spaces. We have V, W, and many others. Okay, we have vector spaces. Then we said, okay, now let's look at functions between vector spaces. Those were linear maps. Okay, now let's take even one step up. Let's look at all the functions between two given vector spaces, and that's going to be again a vector space, whose elements are functions between vector spaces. And you might say, wow, that sounds like abstract nonsense. You can do that forever. But no, it's important, and we're going to see and talk a bit about it. It's a vast topic again. We're only going to touch it, but I think it's interesting and important.